to the last talk of this session, which will be presented by Dr. Gareth Tribello. He is currently a senior lecturer at the School of Mathematics and Physics at Queen's University, Belfast. And his recent research interest is using machine learning algorithm to understand high-dimensional molecular dynamics data and to enhance the rate at which the phase space is sampled in connection to biomolecules, materials, and clusters. And title of his talk is Reconnaissance Metadynamics Writes Again. Good.
Okay, so thanks very much for the opportunity to give this presentation, and thanks to people for sticking around to the end of the day. I know it's quite late, I think, over in India, so I really appreciate you staying up. So what I wanted to talk today about is some work that I've done recently in collaboration with Federico Ghiberti and Michele Ceriotti. And when I think of this work, it's sort of a revisit of something that we did 10 years ago. And so I want to talk about it in that context. But before I get onto that, I want to tell you my favorite science story from the COVID pandemic. So let's just go there. So I play clarinet in a wind band over here in Belfast. And when this COVID pandemic started, I was really worried about going to rehearsals, because what I thought was, there you are playing in a wind band surrounded by all these wind instruments, and everyone is going to be blowing loads of COVID outside of the instruments, and everyone is going to get extremely sick. Other people are more curious than I was, and there was actually masses of research done on whether playing musical instruments spreads COVID. And what they found in this research is actually that the airflow out of most musical instruments is extremely low. And actually, there's very little chance that musical instruments spread COVID. And at this stage, you're probably thinking, wow, 2 years of lockdown have driven Gareth completely and utterly bonkers. What on earth is he talking about? But this is related to my talk, because when I found that out, I thought, really, this is something that I should have known. I mean, if you think about, what's happening there? Why is it not? Ah, yeah. If you think about the shape of like a trumpet or something like that, it's all bendy and the air is going to slow down as it passes through that mess of bends and tubes. And it actually turns out that if you blow through a trumpet, you can't even blow out a candle with the airflow. And I felt like this is something that I should know. And when Michele and Federico came to me and described this idea for this new algorithm that they developed, which was sort of inspired by this reconnaissance metadynamics things, I had that same feeling. So what I wanted to do in my talk was explain a little bit about what we did with the reconnaissance metadynamics, how this has been updated, and sort of what that feeling of this is something that we should have known was about, in the hope that that might be useful to people, because I think it's easy when you're using these complicated machine learning algorithms to sometimes forget simple things. So I will try and show you how we did that with the development of reconnaissance metadynamics. So with that in mind, I'd like to take back in time 10 years, there we are, to the way that I was presenting my work in 2010. So I do these metadynamic simulations, these enhanced sampling methods that are based on biasing. And when I think about these and think about sort of classifying the ones that I really know about, I think in terms of there are two decisions that we have to make. So the first is, what collective coordinates are we going to use? And then the second question is, how are we going to distribute bias along those collective coordinates? And I break this space up into this area up here. We're going to decide what collective coordinates we're going to use using basically thinking, a carbon brain, and we're also going to decide how to distribute the bias along those coordinates by thinking, and that's a kind of umbrella sampling method. And the nice thing with metadynamics in theory, or at least as I supposed in 2010, is that the thinking about how to distribute the bias, you delegate to the computer, because the computer looks after that for you. So what I thought naively in 2010 was you can use these machine learning algorithms to also discover your collective variables. You then combine that with metadynamics and you end up in this sort of nirvana where the computer is doing all the thinking for you, and all you have to do is run the computer, do the analysis, write the paper, and bask in the glory. So that was what we were trying to do. And the way, so how are we actually thinking that we're going to do this? So imagine that I ran a simulation of this Leonard-Jones 7 cluster. What you would see, and this is a movie, but for some reason it isn't working, I don't know why, sorry, is it wouldn't fluctuate much around that minimum. And we know why that is, why we see those boring dynamics. We know that there is an energy landscape that looks something like this. There's a big barrier, we're stuck in a basin, and we're just fluctuating around that minimum. And our idea was, okay, this is really boring. We want to see the rare event, but we're finding out something from those boring dynamics about that basin. We can take the information in some high dimensional space. We can calculate ensemble averages, even if we have a short trajectory. We can also calculate fluctuations, and we can use that information on the average position and the local fluctuations to define some sort of bias that we can then use, and that targeted information to basically eliminate that basin from consideration and to force the system away from a particular configuration. And that was our idea starting out with the development of this method. Sorry, I've got a bit of a sore throat. So that was where we started, but what we saw very quickly with these things was behavior like this. So we actually saw basin hopping events in these simulations, and it no longer became meaningful to fit that dynamics using a single Gaussian. And really that's the first point where this should have given us pause. So I'll let you think about that as I carry on talking to see if you can work out what the conclusions are. But we still had this idea, so that we could fit the local distribution with these Gaussians, and actually the fact that we're seeing between multiple basins wasn't a big problem, because we could use a sort of Gaussian mixture model to fit the dynamics instead of fitting it to a single Gaussian. So I've got a movie here showing you what we did. In this figure, you've got an energy landscape there, which is the contour plot. Then you've got a series of fine points that I hope you can see. Those fine points come from a trajectory that we've run on that energy landscape. So that's the information that then goes into our Gaussian mixture model. And what our Gaussian mixture model does is essentially says, right, take that trajectory, so those little gray dot, those little sort of black dots, and fit that distribution as a sum of Gaussians, okay? And what you can see is that when you fit that distribution using a sum of Gaussians, you nicely find that the Gaussians that come out of that fitting sort of correspond to the positions of the minimums in that energy landscape, even though, as I said at the start, we've not really provided any information about that energy landscape other than through the trajectory to our algorithm. So how does that work in the context of the algorithm? So we all know how metadynamics works. So it's an extension of MD. We know that in MD, you calculate the forces and then you move the atoms according to those forces. And all you do in metadynamics is that every now and again, you make some change to the potential. So you add a Gaussian in these methods. So our idea was, in addition to doing the metadynamics things, what you're going to do every now and again is collect the trajectory and do this cluster analysis on the trajectory, and that's going to identify you new CVs to bias and to force yourself away from. So putting that all together, here is how reconnaissance metadynamics works in all its glory. So you run a molecular dynamics simulation. You see that during that molecular dynamics simulation, you're trapped in a basin. You then run the clustering. You identify that basin. You add bias when you're within a certain distance of that basin, and thus quickly eliminate it. And thus you can go and start to quickly explore these other features in the energy landscape. So you see, we're quickly exploring each of those features one at a time. And if we allow this movie to run on, we eventually get to a sort of flat potential and rapid diffusion all over the place. We eliminate each of those features one in turns through this process of alternating running dynamics and then clustering. Okay, so I don't need to carry that on. Hopefully everyone's got the idea. So that's it on a 2D potential. We also did a study to test it. We did a Lennard-Jones 7, but we tried to make this problem more difficult by basically supposing that each of the atoms was indistinguishable. So we used 7 collective variables here, basically the coordination numbers of each of those atoms. And again, we're doing exactly what you've said before, but now we're doing the clustering in a 7-dimensional space. And we're identifying these features. And the important thing to realize is that this structure that has the yellow atom in the center, in our representation of that data, is different from the structure that has the blue atom in the center because we haven't taken into account interchange symmetry. Okay, so hopefully that's enough of that movie for you to get the idea. So what I think was the main result that we showed in that paper was this figure here, and I still think this is cool. 10 years later, what we've got here is each of those planes represents the basins that we found by doing the clustering that have a different atom having the largest coordination number. So these are the first plane is the one, atom 1 has the largest coordination number, the second plane, atom 2, has the largest coordination number in those structures. And then we've got some simplified representation of that. And what you can see, which I think is quite impressive, which I think is impressive, is that we really have kind of identified, we're seeing that each of the sets of basins that we find in each of those clusters are similar. So we're identifying the same features when we run this algorithm. We're identifying that there is the indistinguishability when we run this reconnaissance metadynamics algorithm. So there's definitely something in using these Gaussian mixture models in combination with a sort of metadynamics bias. But we sort of tried it for this system. We tried it for proteins in vacuum. We did a bit of more stuff with some bigger clusters. But when we tried to take this to studying proteins in water, we never really could get anything sensible out of this method. And so we sort of abandoned it and left it as a sort of dead end. But Michele and Federico have repurposed this in the last year. So now let's talk about what they did to repurpose it. And I think this process of repurposing, oh, sorry, yeah, no. So, and I need to talk about why I think we abandoned it and why we felt that maybe this wasn't such a great idea, which is the fact that there was this thing that we had to do, this fudge that we had to introduce in the method that was slightly dubious. So what I showed, these are some stills from the movie before that I showed you earlier. So what I said we were doing was, we run the dynamics, we collect the data, and then we do this clustering and we identify these basins. And then what we do is we start depositing bias when we're within a certain cutoff of the center of the basin, because we know that the distance from a point becomes a worse CV as we get far away. And we use the hard cutoff for that distance. And what you'll see in the movie is that these basins kind of expand. So the size of that hard cutoff changes. And the reason that we have to expand those basins is that if we don't, what we see is behavior like this. So you deposit a bunch of bias here, and that creates a load of minima around there, which is then a mess when you try to do the Gaussian mixture model. Now, that's a figure from the paper, so we were completely upfront about the fact that we were doing this. But it was always a bit kind of question, there was always that question mark about whether or not this was a good idea and how to set the parameters associated with the expansion of these basins. And that's why I think it sort of hit a bit of a dead end with this method. So if you look at the literature, other people have used these Gaussian mixture models in the umbrella sampling community. And the way that they generally use them is they take that Gaussian mixture model and they use that as a representation of the histogram. So they say, okay, we'll fit this Gaussian mixture model, and then that Gaussian mixture model is a representation of the probability distribution that we're sampling, and then we can use that as a bias. So they actually recognize that what you fit with the Gaussian mixture model is a probability distribution. And I think that's the first step in this new method, Atlas, that Federico and Michele have developed and that I've implemented in Plumed. We write explicitly that what we're fitting is this probability distribution that looks something like this. So in this expression, just to be clear, these are normalized multivariate Gaussians, the G's there, and we've got a sum over those. We've then got a weight for each of those Gaussians. These weights obviously sum up to 1, and that weight tells us how much of the trajectory is in each basin. And then we have this final quantity, pi0, which is a sort of background basin, if you will. So it's some quantity that tells us whether or not we're not near any of the Gaussians that are there. So I'm illustrating it with that, that outer Gaussian. That's a little dishonest because this does not really correspond to a mode in any of the features. So we use that expression. So with that probability distribution in place, what you then do is you sort of fuzzify the basins. I'm just going to move this for a second so I can actually see my slides. So you fuzzify the basins using this expression here. And if you look at that expression, the top line is a probability. So this is the probability of the data point being generated by the kth Gaussian. Just me, what the hell? This is the bottom line is the total probability. So this thing looks a bit like a sort of Bayes theorem. And this quantity here that you get out is then the probability that point S is in the kth feature. So if you calculate this for these 3 different modes here, for the square point, what you get is that phi1, the blue, is equal to 1, and phi2 and phi3 are equal to 0 because you're inside the blue basin. For the circle point, you get that phi1 is equal to 0, and phi2 and phi3 are equal to half, and then the last one gives you a third each. So what we then do is we use that to construct a local bias. So we build a local bias that looks something like this. The total bias is just a linear combination of some local biases, and those local biases are weighted by this fuzzified switching function that switches between our various different basins. And what are these local bias? So you, again, if you calculate the total bias at this time, you see that you get a contribution from those 3 local biases in accordance with where you are relative to each of them. So the form for this local bias looks something like this. If you look at this expression, this is a sum over the history. This is our beloved well-tempered factor. And this is a Gaussian centered on the instantaneous value of a local CV. So those first three terms are basically just your familiar things from metadynamics. And then this final term here is basically splitting the weight of that Gaussian between the features that you've identified using your Gaussian mixture model, okay? So what are these local biases? Well, this S that comes in here is just a vector that contains a lot of CVs that might be of interest. And then to calculate this CK, we could do something like this. So this is going to be the center of our features. So the local Gaussian, the multivariate Gaussians that we've identified. And this here is a local covariance matrix. So this whole expression is a Malinowitz distance. Or alternatively, what we can do is we can diagonalize that local covariance, put the eigenvectors in the numerator like that, and the eigenvalues, square roots of the eigenvalues in the denominator. And this quantity then is basically the projection of on the principal eigenvectors of the local covariance. Okay, so putting all of that together, let's have a look at how the method works in 2D. So here we've got a 2D energy landscape that we're going to investigate. We fit that using a Gaussian mixture model. We take a trajectory from that, fit it using a Gaussian mixture model. We might get something looking like this. So you see we've got 3 Gaussians that correspond to our 3 features. And the collective variables that we're going to use here are represented by those arrows, which are the principal eigenvectors of those local covariance matrices. So this shows you the theta values as a function of time. So you see that during the trajectory, you basically switch between these different modes, and those switchings are almost instantaneous. And then last but not least, this is how the bias grows. And if you've done any metadynamics, this looks a lot like how a metadynamics bias grows in general. The points here are colored according to basically the value of the local bias that you're calculating, because the bias is the sum of these 3 local biases. So you see initially you're inside this red basin, so the bias is felt as the local bias for the red basin. Then you switch to the purple basin, so you build up bias in the purple basin, and so on throughout the simulation. Okay. And the really nice thing here is that in the last 10 years, reweighting of metadynamic simulations has moved on. So we can now extract the free energy from these calculations using reweighting, which we could never do with reconnaissance metadynamics. And in fact, this first figure that I showed you here, the black lines are a reference calculation that we did with parallel tempering, and the purple lines, the filled contours are the free energy surface that dropped out when we did the reweighting of the metadynamics. And you can see that these two things, these two estimates of the free energy are very, very close. Okay, that's great. 2 CVs is wonderful. It's lovely to study these model systems, but it's hardly impressive. But we can go to 6 CVs. So we've got, again, an analytical potential that we've done in CVs. We weighted it down to 2 of them here. And you can see, again, if we compare the parallel tempering result with the result that we get from the reweighted Atlas simulation, we're at a pretty good match. You can also look at the convergence. So here we have measures of convergence. We've got various flavors of Atlas there, which are the rapidly converging ones. The only thing that's really interesting in that diagram is how much faster that we converge than 6-dimensional metadynamics. It's not surprising. No one would expect metadynamics to work particularly well with 6 CVs, but this Atlas thing works much better, and we actually can get meaningful free energies, even in these high dimensional spaces. Sorry to brush over the details there. If people are interested, I can send you the references. What about real systems? So here is, we've done Leonard-Jones 38. So we've done this with 8 collective variables. We've got 3 free energy surfaces here. The red dashed lines are from metadynamics with 2 CVs. The contours are from a parallel tempering reference, and the solid plots are the Atlas with 8 CVs. And what you can see is that the Atlas is getting much closer to the parallel tempering reference there, which is very nice. And these points here that I've illustrated, these are the centers in our Gaussian mixture model. Now, at this stage, you're probably saying, yes, but in order to do this, you need to actually have a trajectory that has explored all of phase space. And that's the whole problem, is getting this thing to explore phase space in the first place. If you have that, then the problem is solvable. But this is actually where this Atlas thing is really neat, because we aren't reliant on good sampling to fit, we are reliant on good sampling to fit the CV, but we can iteratively refit the Gaussian mixture model using a method, something like this. So we start off with an unbiased simulation. We produce a Gaussian mixture model from that unbiased data. We then do the atlas for a while. And then we redo our analysis, having reweighted that free energy surface and create a new atlas bias. And that's precisely what we did for this Leonard-Jones 7 problem. So we actually did 3 rounds of iterating this thing, this method, the different calculations. And the really nice thing, I think, is that if you look at these formulas, you have this pi0 term, and you can calculate a corresponding θ0 term. And this θ0 term is basically telling you whether whether there is a high probability that you are not close to any of the features that you've identified with the Gaussian mixture model. And if you find that the sort of time interval, so the amount of time you're spending in configurations where that value is high, is large, then what's that suggesting to you is that there is some feature in that space that is a kinetic tract that you've not identified, and you probably should go and refit the Gaussian mixture model in order to identify that feature so you can put a suitable local bias there. So this is, I think, a really nice feature of the method, because it means that as well as being able to sort of converge the free energy surface, you can also think about, there is a parameter that helps you converge the CV. So one final example, just to show that it works for proteins. We ran the proteins using all, this is ALA4. We ran using all the backbone dihedrals for this system, but you can reweight out as a function of number of hydrogen bonds and radius of gyration. That's no problem. But another nice feature is that if you don't really know what CVs to use, what you can always do is calculate the relative free energies of the features that you've identified using the Gaussian mixture model, and get some idea of the relative free energies. So that's this atlas idea. I just want to finish by coming back to this business of the musical instruments and COVID. So why do I think this story is like that? Well, if you remember, what I said is that, you know, it should have been obvious that there's not high airflow out of a musical instrument. That's what I felt like. I heard Simon Rattle on the radio. He said, you know, what comes out of a musical instrument is sound and not air. So what's the deal with this reconnaissance metadynamics thing? Well, if you think about how metadynamics works by accumulating histogram and using that histogram to bias the sampling. That's what we say. It doesn't work by eliminating minima and basically forcing you out of them, as I sort of started off with. And if you think about what I've told you about how reconnaissance metadynamics works, and you think about that in terms of trying to define a histogram, the problem there was that we hadn't defined where all the points would go in the various bins. So, you know, there were large portions of trajectory that weren't going into any bin in our histogram. So, you know, that's why I say this problem. This is what I felt when they told me about this method was, oh yeah, of course, you need to basically calculate your histogram properly. So, you know, even though we now use all these fancy machine learning methods, don't forget the basic ideas. So with that, I'll just thank my collaborators as well, because the other similarity between this work and my clarinet playing is that I've had to do my clarinet practice for the first time in about 20 years during this COVID pandemic. I am horrible. No one should listen to me play on my own. The same is true with science. So I really have to acknowledge Michele and Federico, who did all the work here, and everyone who's ever added any functionality to Plume. And with that, thank you, and thank you for your attention.
Thank you for this wonderful talk, Gareth. We have one question in the chat box. Satyabrato Bandyopadhyay. He has said, how can we determine the optimum value for the number of Gaussians in case of Gaussian mixture metadynamics?
So you can look at the paper but there are these because I can't remember exactly how we did it for this one, but when we were doing reconnaissance metadynamics, there are these Bayesian information criteria and there's another information criteria, and these work by basically when you increase the number of parameters, the model will always improve. But what you do is you do something like Occam's razor and you add in a cost for adding in more parameters. So by adding in more parameters, you're making the model more complicated, and then you remove those.
Yeah, also he asked something interesting, that whether you can actually get the kinetic information as you get it from single Gaussian metadynamics run.
That isn't, can I get kinetic information? That is an interesting question. We didn't try, but in theory, yes. And again, I think if you take those features out, that's a sort of natural way of thinking about what the kinetics of transition between those various features. Can I add one other thing that I forgot? I meant to say in my talk.
Okay, sure, go ahead.
Yeah, so I actually have a position available at the moment. And if anyone is looking for a job, please do get in touch. I will post the advert in the chat in a minute before the end of this meeting.
Okay, so is it a position for postdoc or PhD?
It's a postdoc position.
Okay, great. So the next question from Andrew.
I really enjoyed it. I just wanted to sort of come back to something you mentioned earlier, that reconnaissance metadynamics had a bit of a problem with explicit solvent, and I was wondering if the new method sort of helped solve that.
We haven't tried it on a protein with explicit solvent. I think it's not necessarily that the problem was with explicit solvent. I have this question, and I never really know I don't know how to answer it, but I think some of these systems are very easy to solve. It's very easy to get out a good sampling, even if you put in a terrible bias. Now, I have no way to measure what makes a bias terrible and what makes a problem easy or difficult to solve. I think it's an interesting question. Like I said, no idea how to answer it. But yeah, some of these benchmark systems that we do, I mean, for example, like the Leonard-Jones 7 example, if you do that as a function of the first, the second and third distribution of coordination, second and third moments of the distribution of coordination numbers, I have done this putting in what I know are terrible biases that make absolutely no sense, and I still get sampling of all those different configurations. And I think the problem when you go to the explicit solvent is, your bias is, the system is more sensitive to a bad bias, if that makes sense. But I don't know how to quantify that. If you've got any ideas, I'd be fascinated to have a talk, because I think it's an interesting sort of thing.
Okay, so Nishan, please go ahead.
Hi, Gareth, very nice talk. Have you tried to couple this with some replica exchange techniques? Maybe to have multiple replicas exploring, because this would be working pretty well, right, with your technique?
Yeah, we haven't tried it with multiple replicas, but that's certainly something that can be done in the future at some point.
I have one more question, Bima.
Yeah, go ahead, please.
Gareth, maybe also just, if you could also try on some of the toy systems like tripeptide or pentapeptide, we could also compare. We are generating a lot of reference data for these systems, and so our record is that in 1 nanoseconds we have quite a good converged free energy surface into 4D space for revealing tripeptide. So I'd like to see if it can be compared with your technique, and maybe something we can communicate. Because this tripeptide, pentapeptide, I think these are very good systems to try, and where we can try this replica exchange as a reference, compute L2 error, on the replica exchange data. So we have some microseconds data also on these systems. So we could compare it, and we can use this as a benchmark system for other techniques as well.
Yeah.
There are only very few techniques for looking at high dimensions, right? So
yeah.
worth establishing. Okay, thank you.
Okay,
so Gareth, am I right in understanding that basically you are completely trying to bypass figuring out the slow collective variable problem and saying I will just deal with as many collective variables I need?
Yeah.
But if you are missing out on something slow, you are not solving that problem, right? You just need to.
No, exactly.
Yeah, that's for sure. Okay, so thank you, Gareth. And